Hey, Dr. O here, and welcome to Chapter 5. In this chapter, we will begin our two-part exploration into the world of chemical bonds. So let's take a peek at what our objectives are for this chapter. So what can we expect to learn in this chapter? Well, we're actually going to cover quite a bit, starting with electronegativity. So we're going to learn about electronegativity, define it, and see how it plays a role in forming chemical bonds. And next we're going to be looking at the types of bonds that can be formed. And then from there we're going to be writing Lewis structures for some of these compounds that we're forming. And we're going to learn a little bit about resonance structures. And then we're going to shift gears a little bit, and we're going to learn a little bit about formal charge and what that tells us about the way atoms come together to form molecules. And then finally, we're going to learn a little bit about VSEPR, or the valence shell electron pair repulsion theory, and how that plays into molecular geometry. So that's a lot. Let's get started. In order to study chemical reactions and understand them, we need to have an understanding of this principle of electronegativity. And in order to know about electronegativity, we first have to be able to answer the question about which subatomic particle drives chemical reactions. And that would be our buddy, the electron. So it is the movement of electrons around, whether it's the sharing or the transfer, that's going to create these things that we call chemical bonds. Now, another thing we need to understand is why atoms bond in the first place. What drives the atom? What is its motivation? What is the motivation of one atom to couple up with another one? Well, one of those motivations has to do with the lowering of energy. So oftentimes when you have an atom, the system of energy to maintain just an atom is actually greater than it is to maintain that atom if it were in a union with another atom. So that's what we mean by it lowers potential energy. So usually the creation of a union is a lowering of the energy in that system, the system of the atom. Another reason why atoms bond is because it creates stability. Oftentimes what is happening when we create bonds is we are fulfilling the valence electrons. We're creating the octet, maybe even the duet, depends on what atom we're dealing with. So these are two very compelling reasons in nature why atoms would come together and create unions. So then, what is electronegativity? Well, it probably has something to do with electrons, and indeed it does. Electronegativity is the ability of an atom to attract electrons. In fact, we can actually think of it as the ability of an atom to hug its electrons in, and how tightly it hugs those electrons in. Now, when you look at electronegativity, you're going to notice when you're looking at the chart, a periodic chart with regard to electronegativity, you're going to notice some trends. And in this particular chart, they're showing you electronegativity here. And fluorine is going to be the one that has the greatest electronegativity. It comes in with 4, electronegativity with 4. And then hydrogen's over here, comes in at 2.1. Now, if we go to the next, actually let's just skip down. Let's go to this row right here. This row right here, starting with potassium. Now, potassium comes in at the lowest electronegativity in this row, and we end with the highest electronegativity right here, which I believe is boron. And that's true with any of these rows. And so what can we conclude about this? Well, we can say that elements on the left-hand side of the periodic table have a lower electronegativity than the elements on the right-hand side. Well, what is the significant feature between difference of features between the elements in the left-hand side of the periodic table than those in the right? Well, it has to do with the size of the nucleus. So the electronegativity is going to increase across a row when we have atoms with larger nuclei. So that tells us that the positive protons in the nuclei are going to create some of this pull that is driving electronegativity. So the more protons we have populating the nucleus, the greater pull, the greater electronegativity, the greater ability the atom has to hug in those electrons. So that's one thing that we're going to notice. And because the elements on the left-hand side of the periodic table within a row are going to have smaller nuclei than the elements on the right-hand side of the periodic table, the elements on the left-hand side will always have the weaker electronegativity compared to the elements on the right-hand side. All right. Now, the other thing that we notice is if we go down the row, go down a column, whichever column it is, we see a decrease in the electronegativity. So, for example, in the first column right here, we know that hydrogen comes in with the highest electronegativity of 2.1, but it decreases quite a bit by the time we get to the very bottom of that column. And the reason why we see that trend, the decrease as we move down the column, is because every time you move down a row in the periodic table, what are you adding? You're adding another orbital. So you're adding electrons that are further away from all that positivity that is being added into your nuclei. And so ultimately the effect of all that positivity is going to be diminished because the electrons are so far away. So electronegativity decreases as we go down a column, and electronegativity is going to increase as we go from left to right across a row. In this image, we can see the numbers a little bit better, bigger image here. And the thing that you're going to notice is that fluorine has the highest number. It has the greatest electronegativity of all the atoms in the periodic table. And in fact, it's actually nitrogen, oxygen, and fluorine that I like to call the electron hogs, because and the same thing can be said for chlorine, that these atoms, when they're in an area, if there's electrons to be had, they're going to get them. That's pretty much it, because these guys have such a strong electronegativity. So what's happening in the scenario with these particular atoms is that we have just enough orbitals with the electrons positioned close enough to the particular size of the nuclei with the population of protons in there that it just creates this perfect storm of electronegativity. Now, like I said a moment ago, if we move down a column, we're going to notice that the electronegativity actually decreases, and that's because every time we add a row, we're adding another orbital, and that orbital is going to be further away from the nuclei. So that's why when we get down to the bottom of a row, we never see that number being anywhere near what we saw at the top of the, bottom of a column. That's why we don't see that number being anywhere near what we see at the top of the column. And that's going to be true for all the columns. But yeah, right down here, the upper right, nitrogen, oxygen, fluorine are classified as the electron hogs. They're some profoundly electronegative elements, and we can include chlorine in that as well. Now, if we look at the first column, we've got hydrogen. Now, hydrogen is kind of interesting. Hydrogen only has one proton in its nucleus. It has that one potential to have that one electron, and it can share up to two. That's kind of the story of hydrogen. But if we look at what's happening down the row here, it's a big disparity that we see even between hydrogen and lithium is the next one down as far as electronegativity. And again, that has to do with just the dynamic that gets created by adding another orbital and another couple of protons. That's really what is creating these numbers. All right, so as we look at what's happening, we can see that we've got these decreasing values going down a column. I'll give you a moment to look at that. And for the most part, because remember, this is trends, this is not, etched in stone, but it is a trend. We can look at the elements and their electronegativity going across any row, and we're going to notice that, generally speaking, those values are going to be smaller on the left-hand side and larger on the right-hand side. Now, when you get into the middle of the periodic table, it's kind of like crazy man land, is what I like to call that. You'll notice that you've got a couple of areas where the electronegativity kind of stalls out, maybe tops out, drops back down, and then starts to make its way back up again. Right? And even between copper and zinc, you see a big drop there, not a big drop, but a drop, and then it comes back up. So keep in mind, we're talking mostly trends. We want you to have an understanding of the trends, and the trend is, generally speaking, lower electronegativity on the left than compared to the right, higher electronegativity at the top of a column compared to the bottom. Electronegativity chart come to be? Well, Linus Pauling, one of chemistry's greats, was taking a look at chemical bonds, and he knew the bond energies for homonuclear diatomic molecules. For example, the bond energy holding two hydrogens together is 436 kilojoules per mole, and the bond energy holding two fluorines together was 155 kilojoules per mole. Now, based upon what he knew, Pauling surmised that a molecule of hydrogen fluoride might have a bond energy that was the average of the two bond energies of the homonuclear species, which in this case would be 296 kilojoules per mole. And if the experiments demonstrated that this was true, then he could conclude that the hydrogen fluoride bond was covalent, meaning that the hydrogen and the fluorine were sharing the electrons somewhat equally. Well, that didn't happen. And in fact, experiments showed that the bond energy for the hydrogen and fluoride atoms was considerably higher, coming in at 565 kilojoules per mole. Now, from this experimental data, Pauling concluded that the hydrogen fluoride bond must be more ionic in nature, meaning that the electrons at play, the electron between the two atoms, the hydrogen and fluorine atoms, was actually transferred from the hydrogen to the fluorine. Now, why would this be the case? Well, take a look at fluorine's electronegativity right here. It is the highest among all the elements. So yeah, it totally can strip that electron from the hydrogen and make it its own. You to use this information. How do I want you to use this chart? Well, let's say that we had a bond between oxygen and hydrogen, such as a hydroxide ion, or maybe even one of the bonds making up water, because remember, water is made up of two hydrogens and an oxygen. What sort of bond do we have here, or what is its electronegativity value? Well, the way we would calculate that is we would look at the electronegativity value for oxygen, which comes in at 3.5. That's just a number. I'm pulling it off the chart. And then we look at the electronegativity of hydrogen. Just pulling it off the chart is 2.1. Now we ask ourselves, what is the difference between these two elements? What is the electronegativity difference? Well, we would take the larger value and subtract the smaller value, and we end up in this case with the electronegativity value of 1.4. So we could basically say that the electronegativity of the oxygen-hydrogen bond is 1.4. What if we had something that we knew was ionic in nature, such as sodium and chlorine? Well, we'd run it through the same scenario. We would look at the electronegativity for sodium, which comes in at 0.9, and we do the same thing for chlorine, which comes in at 3, and we subtract the smaller value from the larger value, and we end up with an electronegativity value of 2.1. So we can see that it is a larger number, a larger electronegativity number for sodium chloride than it is for the hydroxide ion. So what is that telling us? Well, that becomes the next important thing, which has to do with defining what type of bond we're looking at. And that's going to relate to this chart right here. So in this chart, the electronegativity difference, this will give us an idea of where our bond is falling with regard to whether it is covalent or whether it is ionic. It'll also tell us that if it's covalent, whether it is nonpolar or whether it is polar. And let's take a look at this. So here for the hydroxide or the OH bond, we see that it comes in at 1.4. Well, 1.4 falls within this region right here. And here is when we're going to have a situation where we're going to have an unequal sharing of the electrons. And in this case, because oxygen has a fairly large electronegativity and hydrogen has kind of a mediocre one, not a weak one, but not a real strong one, then we can know that oxygen has a greater ability to take those electrons, hold on to them, and hug them in tight. So most of the time, the electrons are going to be hovering around the oxygen. So in this scenario, this would be an example of our oxygen, and this would be the example of the hydrogen. So in an OH bond, the oxygen is always going to have a slight negative charge, and the hydrogen is always going to have a slight positive charge, and that makes it polar. So for the OH bond, we could say that it is polar and it is covalent. It's a polar covalent bond. Now, if we come over here and we look at what we have with sodium chloride, it comes in at 2.1. And if we look at the scale, we can see anything greater than 2, maybe even 2 and greater, is considered an ionic bond. And we do happen to know that sodium chloride is ionically bonded, because when we drop it into water, we can see that it dissolves, and the reason why it's doing that is because it's being absorbed by all of the polar bonds of water. So that's a little bit about that. So we've taken a peek at what a polar covalent bond looks like and an ionic bond looks like. But what about this pure non-polar covalent bond? Well, what would give us that sort of, let's go ahead and fill those in, that sort of a scenario would be something like this hydrogen molecule. This is one of those homonuclear diatomic molecules that Linus Pauling was working with. So if we were to run the numbers with this, well, we know that one hydrogen is going to have a value of 2.1, and the other one is also going to have a value of 2.1. And if we subtract 2.1 from 2.1, we're going to end up with 0, and 0 falls right here on our electronegativity difference scale, which clearly puts it within the realm of pure polar covalent bonds. So in the case of pure polar covalent bonds, you're going to end up with two atoms that have very, very similar electronegativity, so that that difference between them actually ends up being less than 0.4. So this is how I want you to be able to use the electronegativity scale. So for example, if I were to give you a problem such as tell me about the nature of the nitrogen-hydrogen bond, I would expect you to come to the electronegativity chart, find the value for nitrogen, find the value for hydrogen, do the subtraction, and then look at this chart right here and tell me, is it polar covalent, is it ionic, or is it non-polar covalent? That's how I want you to use this information. Previously, we learned how to write Lewis dot structures for elements such as oxygen or carbon. And we did this by counting the valence electrons and dropping them in on each side of the element's symbol one at a time, like we see with carbon, or until we had to double up if we did 4 and then we had maybe a couple more doubling up, like what we see with in oxygen, where we have those two electron pairs. But how do we draw Lewis structures for molecules such as carbon dioxide or polyatomic ions such as ammonium? Well, let's see. Okay, so there are rules for writing Lewis structures for molecular compounds, and they're going to be a little bit different than the rules for writing structures for polyatomic ions. We're going to start by taking a look at how to write the structures for molecules. So what is it that we're going to have to do first? Well, the very first thing that you need to do is you need to write a correct skeletal structure for your elements. And what does that mean? Well, it means that you need to have the elements positioned in roughly the same arrangement that Mother Nature would place them. And there's a couple of rules for that. So for example, hydrogen, it can only bond with one other element, so it's always on the end, or it's always terminal. That's what we mean by terminal. It's always on the end. So then the next question might be, who goes in the middle? Well, usually it's going to be the least electronegative element that goes in the middle, which means that if you have a more electronegative element, those are also going to be placed on the ends or terminally, just like hydrogen would be. Sometimes they're even coupled up with a hydrogen. So let's take a look at an example to see how these rules apply, this first rule and its little sub-rules. So we're going to start by looking at carbon, a couple of hydrogens, and an oxygen. Now we know that hydrogen is terminal, so let's ignore the hydrogens for a moment. And now we're going to have to ask, who is least electronegative? Is it carbon or is it oxygen? Well, you probably don't have that memorized, but the good news is there's a chart in section 5.2, the one previous to this one, and it will tell you who is least electronegative. I happen to know that it's carbon. So we're going to position carbon just so. And now the rule tells us where to place hydrogen, which is going to be terminally around the carbon. So we'll place those two hydrogens. And since oxygen is more electronegative, it will also go around that central atom, carbon. And thus we have created the correct skeletal structure for our molecule. Okay, so we've taken care of our skeletal structure. Now we move to Rule 2. Rule 2 says to calculate the valence electrons that are being contributed by each element. So let's bring back our carbon and hydrogens and oxygen from before. Now we know that carbon is going to give us 4 valence electrons, and hydrogen is going to give 1, but we have 2 of those, and oxygen is going to give us 6. So if we add all of these together, so carbon is going to contribute 4, our 2 hydrogens are going to contribute 2, and our oxygen is going to contribute 6. When we add all of that up, we see that we have 12 electrons. So these are the 12 electrons that we're going to place on our molecular skeleton. Okay, so Rule 3 says that we're supposed to distribute these electrons in order to make octets for each element, except for hydrogen, which only gets a duet. So we know we have 12 electrons, and let's bring back our skeletal structure, and let's start dropping those electrons in. Now the first place I like to start is between the pairs of elements, because that will be what establishes the bond between them. So we're going to put a couple of electrons here, so there's 2 of our 12, and then another couple here, and that's 4 of our 12, and then another couple here, and that's 6 of our 12. Now we have 6 that we still have to place. And we know that oxygen has some electron pairs around it, so let's go ahead and drop the remaining 6 sets of electrons around oxygen. And in this, we have now placed all of our electrons. So let's see what we do next. Okay, let's look at the 4th rule, because there is one, and it says that if an atom doesn't have an octet, then you form double or triple bonds in order to form octets. So if we look at this structure, we can see that our hydrogens both have duets. That's great. We can see that our oxygen has an octet, but who doesn't have an octet? Well, it would be carbon. Carbon only has 6 electrons. So how are we going to amend this for carbon? Well, we can share a couple of electrons that are populating oxygen. So we can move a couple of electrons there. And now, in essence, what we've done is we've created a double bond between carbon and oxygen. And this double bond will allow 4 electrons to be shared between them. So there are 4 electrons for carbon. And then there's one set of electrons shared with one hydrogen, and then another set shared with the second hydrogen. And now carbon also has an octet. And there is a 5th rule. The 5th rule says to double check everything, and that's always a great step in any sort of problem solving technique. But basically, these are the rules on how to draw a molecular, a Lewis structure for a molecular compound. Okay, so let's see what the rules are for drawing Lewis structures for polyatomic ions. Well, the first thing you need to do is write out a correct skeletal structure, which is going to be the same as what we did for molecular compounds. And then we need to calculate the total number of valence electrons, and this is where we're going to deviate just a little bit. Because remember, polyatomic ions are going to have charge. Now that charge may be a positive charge or a negative charge, and remember, those represent something. They represent either the presence or the absence of electrons. So if you have a negative charge, you need to add 1 electron for each negative charge on your ion. Or if you have a positive ion, you need to subtract 1 electron for each charge that's positive. So this is the one variation that we have in polyatomic ions. From here it's the same. Then you want to distribute those ions in order to make octets, and then if an atom doesn't have an octet, then you're going to move electrons around in order to form double or triple bonds. So let's look at an example. Let's take the hydroxide ion, which is OH with a negative sign, which means we now have an extra electron that we're going to have to count for, and we already have our skeletal structures, pretty basic. It's just a hydrogen and an oxygen. So let's count up our electrons, because that's what we need to do in step number 2. So we know that oxygen is going to give us 6 electrons. We know that hydrogen is going to give us 1 electron, but we have that negative charge, and the rule says that we have to add 1 electron for each negative charge, which is going to be that. So when we add these up, we're going to end up with 8 electrons that we have to place around our structure, our skeletal structure. So let's do that now. I like to place a couple between the atoms. That shows the bond that exists. And now we're going to go ahead and populate the oxygen with the rest of the electrons. So we have 2 already in place, 3, 4, 5, 6, 7, 8, and we are done distributing our electrons. Now there's one more step with these, because you need to let your reader know that this is a special structure, that it does have charge. And the way that we do that is we put a bracket around it, and then we also represent the negative charge, or possibly the positive charge if we were dealing with a cation, but in this case it's a negatively charged ion. We put that negative charge right there, and that lets our reader know that we're dealing with a polyatomic ion. So we just finished looking at the rules for drafting Lewis structures for compounds that have at least 2 atoms in it. And in doing this, we might come across a situation where we need to ask, well, what if a compound has 2 viable Lewis structures? Well, that does happen, and when that happens, what we're looking at is a resonance structure. So let's take a look at what a resonance structure looks like and how we're going to deal with that. So we're going to take the ozone molecule. It has 3 oxygens. That's what it's made up of, is 3 oxygens. And we're going to do our skeletal structure, which means we have 3 oxygens in a row. Because remember, oxygen has a tendency to want to be terminal. So 2 of them are going to be on the ends, and then 1 of them is going to have to be central. And next we need to count our electrons. So we know that each oxygen is going to give us 6 electrons, and we have 3 oxygens, so 6 times 3 is going to give us 18 electrons. So we have 18 electrons that we need to place around these 3 oxygen atoms. So we're going to start by dropping in a couple of electrons between the oxygen on the left and the center oxygen, and then doing the same thing with the oxygen on the right and the center oxygen. So I like to make sure that those bonds get acknowledged first. And now we're going to start putting electrons around the terminal oxygens. So we placed 4 of our 18. There's 5 and 6, 7 and 8, 9 and 10, 11, 12, 13, 14, 15, 16. So we've now, we have octets on our 2 terminal oxygens, and we have 2 electrons remaining, so we're going to drop those on the central oxygen. Now if we do the check to make sure that everybody has an octet, we can see that the center oxygen doesn't have an octet, so it's going to have to share some electrons. So let's pick these electrons from the oxygen on the left down at the bottom. So we're going to take those and move them over to the bond between the central oxygen and the oxygen on the left, thereby creating a double bond with the oxygen on the left. Still have a single bond with the oxygen on the right, but now we've kind of changed the configuration with that double bonding with the oxygen on the left. So as I look at this particular structure that we've done, I have to ask the question, why is this oxygen on the left so special that it gets to share in a double bond with the central oxygen? Well, the reality is that it is not so special, and that a double bond is equally likely to occur between the oxygen on the right and the central atom of oxygen. And when we have this, we could draw a two-headed arrow that's showing that these 2 structures are going back and forth, that the ozone molecule is waffling back and forth between having a double bond on the left and a double bond on the right. And this is what we see with resonance structures, two viable Lewis structures. Now, it may be easier to visualize if we eliminate some of the dots and replace them with a single line, which represents an electron pair. So if we look at the molecule on the left, what we see is that the oxygen on the left is sharing a double bond, which is 4 electrons, with the central oxygen, and that the oxygen on the right is sharing an electron pair, which is represented by the single line with the central oxygen. So we have the double bond on the left and the single bond on the right. Now if we look at the molecule on the right, we see just the opposite of this. On the left of the central molecule, we have our central atom, we have the single bond, and on the right we have the double bond. Now the question might be at this point, do these structures actually waffle back and forth? Does it exist over here with this double bond to the left of the central atom and then switch so that the double bond is now on the right of the central atom, or is something else a little different happening? Well, in reality, it's more like this, where we have the atoms in line, we have the lone electron pairs in place, we have single bonds all the way across. And then the electron pair that is creating the double bond in the molecule on the left and the molecule on the right is actually delocalized across all three. So it actually looks more like the structure that you see on the bottom. That is the idea behind a resonance structure, is that you can represent it with these two Lewis structures, and those are viable, and they're going to indicate what's actually happening with this molecule is this delocalization of at least one electron pair. So we just saw an example that it is possible to have two viable Lewis structures as a resonance structure. Is it possible to have more? Well, let's look at an example. So here we have an ion with our nitrogen and 3 oxygens, and we're first going to draw our skeletal structure. That's what the rules say to do. So here we have our nitrogen in the center, it's the least electronegative, and then our oxygens located terminally around the central nitrogen. Now we want to count electrons. So each nitrogen, we only have one, is going to give us 5 electrons. We have 3 oxygens, each one's going to give us 6 electrons, and then we have that negative charge up there, and we have to account for that. And remember where a negative charge comes from? It comes from an electron. So this particular polyatomic ion has 1 extra electron, and we need to account for it just like that. So when we move these numbers to the right, we know we have 5 electrons from nitrogen, 18 from oxygen, and then 1 with that negative charge. And when we add all of that together, we get 24 electrons that we're going to have to place around our skeletal structure. Let's start doing that. And I always like to place a couple between the atoms so that we can show that things are bonded together. And now we're going to populate the 3 oxygens. So we have 2, 4, 6 of our 24 placed. There's 6, 7, 8, 9, 10, 11, 12, there we go, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now at this point we have to check to make sure everybody has an octet, and we can see that our central nitrogen does not. So what has to happen here is it's going to share an electron pair with one of these oxygens. So let's just pick the oxygen on the left. So we're going to take an electron pair from that oxygen, and we're going to drop it in and share it with this nitrogen. Now I've colored these because I want you to see what happens, or what the possibility is, when it comes to the resonance structures that are viable for this particular polyatomic ion. So nitrogen can share 2 pairs of electrons with the oxygen on the left. It can also share 2 electron pairs with the oxygen on top, and then it can do the same thing with the oxygen on the right, thus giving us 3 resonance structures. What we saw with our very first resonance structure, even though we show it with these distinct electron pairs being coupled with the 3 different oxygens and nitrogen, what's really happening is that that electron pair that's being shuffled around is delocalized between all 3 bonded atoms. Now that we've taken a stroll down memory lane about our Lewis structures and the placement of electrons, now is a good time to introduce something known as formal charge. Now, what is formal charge? Well, formal charge is a fictitious accounting system that helped scientists understand where electrons were going to go between atoms when chemical bonds were formed. So what it does is it gives a better understanding about which arrangement of electrons created viable Lewis structures. So for example, if we had carbon binding to a couple of oxygens, carbon dioxide, how do we know that this structure is the preferred one and not that? Well, we can do a little calculation with formal charge and prove that the one on the left is the more stable structure. Or what if we had something like dinitrogen oxide? How could we know that this is the structure and not this one? Well, it's because we can run it through our counting system and figure out if the numbers that we get regarding a charge that would be applied with regard to the electrons that are populating the bonds between these atoms, if they make sense or not. So let's take a look at what's involved in calculating formal charge. So how do we go about calculating formal charge? Well, you're going to want to draft a table, looks something like this. And on the left, you're going to identify the characteristics around the electrons for each element. And the things we're going to be interested in is knowing the number of valence electrons. And then from that, we're going to subtract the number of non-bonding electrons, those lone electron pairs. And then from that, we're also going to subtract half the number of the bonding electrons. And when we do that math, identify these different electrons, and then do the math, we're going to end up with the formal charge. And we're going to do this calculation on every element in our molecule. And the two molecules that we're going to be looking at are two different versions of hydrogen isocyanide. Now, hydrogen is always going to be a terminal element, so it's up to the carbon and the nitrogen to determine what is the right configuration for this molecule. So let's start working the information on hydrogen. So how many valence electrons does hydrogen have? Well, it always has one, and we know that by looking at the periodic table. And we're going to subtract the number of non-bonding electrons. It has no lone electron pair, so we're going to put a 0 there. And then we're going to subtract half the number of bonding electrons. Well, it has only 2 pairs of electrons that it can manage, and those are represented by that single line to carbon. So 2 divided by 2 is going to give us 1. And when we do the math, we have 1 minus 0 minus 1 equals 0. The formal charge on hydrogen in this particular molecule is 0. Let's do the same thing for carbon. Carbon has 4 valence electrons. It has no lone electron pairs, no non-bonding electrons. And it has 8 bonding electrons. So we're going to take 8 and divide it by 2. That will give us 4. So 4 minus 0 minus 4 is also 0. Now let's look at nitrogen. Now nitrogen brings to the table 5 valence electrons. It has 2 non-bonding electrons, and it has 6 bonding electrons. We're going to divide that by 2. So what we have with nitrogen is we have 5 minus 2 minus 3 equals 0. Okay, so let's do this for the second structure. So hydrogen has 1 electron, no non-bonding electrons, and 2 bonding pairs, which is going to give us a formal charge of 0. Nitrogen brings to the table 5 valence electrons. It has no non-bonding pairs, and it has 8 bonding pairs of electrons. And when we do that math, this is going to be 5 minus 0 minus 4. And that will leave us with a positive 1. So there's a positive 1 on nitrogen in this particular molecular arrangement. Let's look at carbon. Carbon brings 4 electrons to the table. It has 2 non-bonding electrons, and it has 6 bonding electrons. When we do this math, we end up with a negative 1. All right, so what structure B is telling us is that if we had the elements arranged this way, our nitrogen would be bearing a +1 charge, and our carbon would be bearing a -1 charge. Now this becomes an important piece of the information that we're going to use to evaluate the likelihood of whether structure A or structure B is the viable Lewis structure, or the viable molecular structure, I should say, for hydrogen cyanide. Because we have to think about who is most electronegative. Because remember, the rule says that the least electronegative element should be placed in the center of your molecule. And the reason why is because they have a tendency to not want to bear any sort of charge. Well, if we look at nitrogen and carbon, carbon is the lesser electronegative element, and we're asking it in this scenario to bear a negative charge. So this is not going to be a viable arrangement for hydrogen cyanide. B is not going to be the one that works. When we look at the formal charge for structure A, all of the elements come in at 0, which basically means that this is the favorable arrangement for hydrogen isocyanide. So that's how you do formal charge. So are there some rules to help us evaluate formal charge? Well, of course there are. The first one is pretty much what we saw in the previous example, that the preferred molecular structure is the one where all formal charges equal 0, where all formal charges on the atoms in the molecule equal 0, as opposed to the version where some formal charges are not 0. So if you should happen to do this and everybody's 0, that's going to be your preferred structure. Now sometimes that doesn't happen. Sometimes you don't have zeros all the way across. Now if there's no possible structure where all formal charges are 0, then the preferred structure is the one with the least number of non-zero charges. The least number of non-zero charges. So that means it'll have some zeros and some non-zeros, and you want the one where there are the fewest charges that are not 0. All right, the adjacent atoms in a molecule should have opposite signs if charges are present. So this is, again, that scenario where you're not able to get zeros all the way across. So when that's the case, you want to make sure that the adjacent atoms have opposite signs, and that'll be your preferred structure. And the fourth thing is that if there are multiple structures that satisfy requirements 1 through 3, then the structure with negative formal charges on more electronegative atoms is preferred. And I addressed that when we looked at hydrogen cyanide, and I said that we were asking carbon, the less electronegative element, to bear the negative charge. Ideally, it would be nitrogen that would bear that charge because it's more electronegative than carbon. But where we have the scenario where we met the first requirement, which is that we have a molecule where all the formal charges are 0. But this will help you in evaluating your work moving forward, giving you some idea as far as guidelines and how you do that assessment with formal charge.